Last week we started to introduce what happens when we mix acids and bases by mixing together strong acids and strong bases. In fact, acid-base chemistry always involves a mixture of an acid and a base, even if one of those is very weakly acidic or basic, like water. In particular, we saw that when strong acids and bases are combined, the hydroxide and the hydronium react to produce water, neutralizing each other. Now we'll take a closer look at what happens when we mix a weak acid and a strong base, or vice versa. Let's start with 250 milliliters, or 1 cup of white vinegar. So this says that it's 5% acetic acid by mass, so that's 50 grams per liter of water. The molar mass of acetic acid is 60.052 grams per mole, so a 5% mass per mass solution is 50 grams times 1 mole per 60.052 grams equals 0.833 moles per liter, or 0.833 molar. To find the pH, we need to calculate how much of the acetic acid is hydrolyzed according to the equilibrium expression. And to do that, we turn to our trusty ice table, and we get 0.833 molar minus some amount produces that same amount of hydronium. And at equilibrium, we can calculate x equals 3.82 times 10 to the negative 3. So the pH is the negative log of that number, or 2.42. So in this case, our cup of vinegar has a pH of 2.42. What happens when we add a strong base, like sodium hydroxide? The first step is the same that we've already seen. The salt is going to completely dissociate into sodium ions and hydroxide ions. When there was nothing but water available as a source of protons, then even if hydroxide did pull one of those protons from water, you would just end up with another hydroxide. There was no weaker base or stronger base in the mix. Now we do have a different source of protons, the acetic acid. So the first thing that those hydroxide ions are going to do is to grab onto one of those protons from the acid and hold onto it. And that reaction is acetic acid plus hydroxide is converted into acetate and water. Between acetic acid and water, water is the weaker acid. So we should expect this equilibrium to favor the products. In fact, as a strong base, we can assume complete conversion from hydroxide to acetate. And now that we've changed the amounts of acetic acid and acetate, we need to revisit the equilibrium expression. For example, let's say that we added 4 grams of sodium hydroxide to the cup of vinegar. So that doesn't change the volume, but it is going to change the relative amounts of acetic acid and acetate. So 4 grams divided by the molar mass of sodium hydroxide gives us 0.1 molar of sodium hydroxide in a quarter of a liter, giving us a total concentration of 0.4 molar of the hydroxide. We can use another ice table to see how this is going to impact equilibrium. All of the hydroxide we added is going to react with the acetic acid to produce acetate. So that means that the amount of acetic acid is going to drop by 0.4, and the amount of acetate is going to rise by 0.4. The amount of water will also change, but not by a really significant amount. Now we have new equilibrium values for both the acetate and the acetic acid. And we can calculate the new concentration of hydronium as 1.74 times 10 to the negative 5, and the new pH as the negative log of that number, or 4.76. What if instead we had added the same amount of sodium hydroxide as we had of the acetic acid? When we added the same amounts of strong acid and strong base, we ended up with a neutral solution, and only the sodium and the chloride ions were remaining. If we add an equimolar amount of strong base as the initial concentration of weak acid, this means that all of the hydroxide is going to react with all of the acetic acid and turning it entirely into acetate. Since there's no more acetic acid, it doesn't really make sense to equilibrate based on the acid dissociation constant. Instead, what we have is a concentration of the conjugate base, acetate. Its equilibrium constant is Kb, and we can find that by dividing the self-ionization constant of water by the Ka to get 5.68 times 10 to the negative 10. Now we can calculate the final concentration of hydroxide in the water, giving us a pOH of 4.66 and a pH of 9.34. So adding an equivalent amount of strong base doesn't neutralize a weak acid, it actually converts it into its conjugate base. And instead of balancing at pH 7, we need to calculate the concentration of hydroxide and hydronium by solving a base equilibrium problem. Before we arrived at the equivalence point, we had a mixture of acetic acid and acetate, so a weak acid and its conjugate base, in the same solution. This creates a pretty special condition that we're going to discuss next time.